I'm going to briefly describe how to use an interactive simulation that models the transient behavior of a tank. And what we're doing is solving the material balances for this system, where we have a first order reaction. So the system is shown in the diagram. We have a volumetric flow rate in with the inlet concentration, and then we have a volumetric flow rate out, which is not in general the same. And this tank is well mixed, so the concentration in the tank is the same as the concentration leaving the tank. And we're solving the material balances for the case where we have the overall material balance, and then when we have reaction taking place, then the concentration of A in the reactor is also determined. And we can plot several things that we'll observe when we look at the actual simulation. The reaction rate constant can be changed, or it can be set to 0, so we can just look at a non-reactive system and see how the concentration changes. Now, as liquid flows into the tank, if the flow rate is higher coming in, of course, the tank level will rise until we reach a steady state. The simulation speed just means that we're displaying the graph at a faster rate, that it takes 6.6 seconds of actual time filling the tank for 1 second of providing the graphing to make it quicker to see what the behavior is. So let's look at the interactive simulation to see how it responds as we change some of these values with sliders. Well, here's the simulation where we've turned off the reaction by setting the rate constant equal to 0, and we set the simulation speed to its maximum value. And we can look at volume versus time. So if we start the simulation, it plots the volume versus time, and then you'll notice the x-axis resets. We also can look at concentration versus time, since we're feeding in a higher concentration than initially was in the tank, and we get the steady state concentration. We also can look at outlet flow rate. The outlet flow rate increased as the height of liquid in the tank increased until, again, we reached a steady state. Okay, so we can also have the reaction rate constant be a large number. And now if I start the simulation, you see the concentration increases and then starts decreasing and eventually would reach a steady state. So the idea of this simulation is to give a better physical feel for how, as volumes changing, concentration changing, flow rates leaving the reactor are changing. And of course, the flow rate leaving is proportional to the height of the liquid. So as the hydrostatic pressure increases, then there's more pressure pushing liquid out through the exit.